Hello guys, hope you're all doing fine. Today we're gonna talk about chapter 9 of the book, which is about stress and strain. Uh, in this video, we're gonna talk about tensile and compressive stress, shear stress, then we will go ahead and talk about tensile and compressive strain and deformation. Then we will talk about shear strain, and at last we will talk about the Hooke's law, which is the relationship between the stress and strain. Okay, so what is tensile and compressive stress? Imagine we have a bar. Let me just write down two bars here. Wait, if we have a bar, if we are just thinking about we have equilibrium, because in the strength of material we should always think about that we have equilibrium, or we are in equilibrium. So if we put a pressure on these two sides of our bar, there is going to be an equal amount of pressure on these two sides of the bar. Call it P. So what is happening on this bar, or what is happening in here? So this bar is in compression. You're compressing this bar, right? What if you're trying to elongate this bar? This bar is gonna be in tension, and because it is in equilibrium, there are some forces inside the bar that are trying to fight these forces. Okay, what happens if this continues, if we keep pressuring this bar? Okay, all agree that this bar is gonna look like this after some times. And if we keep stretching this bar after some time, you all agree that this bar is gonna look like this. Of course, if these forces continue, this bar is gonna break, and this bar is gonna break as well. Okay, so what are we doing here, and what are we looking for? We are looking for the stress, the amount of stress that we can put on each material, and this stress can be calculated by this formula. So sigma equals P over A. So what is sigma? Sigma is the stress that we put on the material, that the material is undergoing because of the forces. Okay, and what's the P? P is external axial load, which is on each material that we are calculating. And what is A? And A is the area of the cross section which the stress is loaded on. For example, if we are talking about this, for example, this is a wooden bar. Okay, if we are talking about this wooden bar, if the load, and if, for example, this is 2-inch and this is 15-inch, if the load is on this side, okay, our A is going to be 2-inch by 2-inch, 4-inch squared. And if the load is going to be on this side, call it A1 and A2, 2-inch by 15-inch, which is 30 inches squared. Right, so A is the cross section area where the force is going to be loaded on our beam or on any material that we are talking about. In US system, sigma is in pound on square inch, or KPSI. And in SI system is in Pascal or megapascal. All right, where we can safely say 1 Pascal equals 1 Newton square meter, or 1 megapascal equals 1 Newton millimeter square. All right. Okay, so our equation today is sigma equals P over A. What if we want to know how much is P? Because this is the equation, we can easily change it to sigma into A. Or what if we want to know how much is A? Can easily say equals P over sigma. Okay, so when do we need these equations? Whenever we need to know how much is the stress, we can use this calculation. Okay, but whenever we need to know how much maximum force we can load on a material before a material breaks, we can use this equation. Okay, for example, I have a beam which is stuck on the wall on the one side. Okay, and I am trying to put a force on this beam and alongside this beam. Okay, so I want to know how much can I put on this beam, how much pressure I can put on this beam that this beam doesn't break. Okay, for example, if the area of the cross section of this beam is, for example, 4 inches square, and the allowable axial stress of the material, or this bar or this beam that I have is, for example, 50 pound. So how much is the maximum force that I can load on this beam that it doesn't break. So we can easily say P equals sigma A. So P equals 200 pounds. So it means that if we put 200 pounds or more force on this beam, it is gonna break. But if we put anything under 200 pounds, this beam is not gonna break. Same as here. Same as here. If we want to know how much should be the cross section of this material, of this beam, that it doesn't break, so we use this equation. And that's why we call this sigma O. So it means that this is the maximum allowable axial stress that we can have on this material. Okay, and now we can safely go and look at the problems or the examples that we have in the book and explain how we can do them individually. All right, guys. So now we want to do examples 9.1. Example 9.1 has two sections. Section A, compute the tensile stress developed in the square steel bar 2" by 2" in cross section shown in figure 9.3. The bar is subject to an axial tensile load of 95 KIPS. So first, the cross-sectional area of the square steel bar is 2" by 2". So 2" by 2". So the area is 4" square. All right, now we can put everything that we have in the formula that we have. So sigma equals P over A. Sigma equals 95 K over 4" square. The answer is 23.8 if we put it in the calculator. K or as we talked about it, this is American way of saying it, we call it KSI. All right, this is for part A. What does the part B say? Part B says, determine the tensile stress or sigma T if the member is a structural steel W8 by 31 and the load is the same, 95 KIPS. So if we go to appendix A of the book, we can figure out the cross-section area of W8 by 31 is 9.13". So everything is going to be the same, just the area of the cross section is going to be different. Sigma equals P over A. Sigma equals 95K on 9.13 square inches, which is 10 point, if we put in calculator, 10.41 KSI. This is for example 9.1. If we go to example 9.2, it says, rework example 9.1, assuming that the steel bar to be 50 millimeter by 50 millimeter in cross section. So this is going to be 50 millimeter by 50 millimeter. And the load with an actual tensile load of 400 kilonewtons. So since the numbers are different, we gotta figure out how much we gotta do it. So the cross section 50 by 50, the load of 400 kilonewtons. So we have P equals 400 kilonewtons, or we can call it 400 and 10 to the power of 3, or 10 cube Newton. So we converted kilonewton to Newton. All right, and our area is 50 millimeter into 50 millimeter, which is 2500 millimeter square, or we can convert it to meter square. 2500 millimeter square is 2.5 into 10 cube force minus square meter. Now let's see how much is our sigma t is going to be. So our formula is the same. P over A equals 400 newtons and 2.5 to minus 3 meters equals 160 power of 10 Newton meters. Or we can convert it to 160 megapascal. Guys, if you have doubt about 10 to the power of 3 or minus 3 or anything like that, if you don't like it, if you don't like this 10 to the power of something, you can easily just write down, for example, instead of 2.5 to the power of 10 to the power of minus 3, you can just easily write down 0.0025. all right, this is because it makes it neat, more neat that we write it down like this. So or simply we can say, since 1 Newton millimeter square is 1 megapascal, we can write it down in this way. Here, sigma t equals 400 to the power of 10 by 10 to the power of 3 Newton, 50 millimeter to 50 millimeter, so we can just call it to the power 2, equals 160 Newton millimeter square, or We all agree that this equals 160 megapascal. Okay, example 9.3. The steel rod suspenders are to support pipes in a power plant as shown in figure 9.4. So these are two pipes, and this is the steel rod supporter that holds these two pipes. Just remember, this is the cross section, okay? Each rod has a diameter of 3/8 inch. So the diameter of each rod is 3/8 inch and has allowable axial tensile stress of 24,000 psi in the body of the rod. Calculate the allowable axial tensile load in each rod. Okay, so if we want to calculate the area, the cross section area of 3/8 inch diameter rod, we can use this calculation. So A equals pi d2 over 4. So pi 3/8, we can just easily say that this equals 0.375 inch square divided by 4. This number, if you want to see how we calculate it, we say 3/8. So 3 divided by 8 equals 0.375. Okay, this number goes here, right? And the answer is 0.1104 inches. Okay, so if you guys remember, the allowable axial tensile equation was, if you want to see how much is the allowable axial tensile stress, we use P equals sigma all A. All right, so P equals, in the question it says 24,000 pound square. And how much is our A? A is 11104 inches square. The answer is 2,000. Just write it down here. 2,650 pounds. It means that the maximum force before this breaks is 2,650 pounds. All right, the example 9.4. The example says compute the required size of a short square dressed S4S timber post shown in this figure. The post is subject to a compressive load of 100 kilonewtons. The allowance axial compressive stress is 5.5 megapascal. So what do we have? We have the load and we have the stress, which is 5.5 megapascal. So what do we need? We need A. equals P all, this is the maximum. Okay, A equals 100, which was megapascal. We can convert it to Newton on 5.50. Okay, sorry, it was kilonewton. We converted to Newton, megapascal. The answer is 10.18. The answer, I'm just gonna write down the answer down here. So the answer is 18.18 in 10 to the power of 3 millimeter square. So what does this mean? This means that if this area, this cross-section area, is this big, it can endure this much power. If the cross-section is smaller than this, the structure is gonna break. And from Appendix E, Table E2, a nominal 150 millimeter by 150 millimeter square timber member has a cross-section area of 19.6 to the by 10 to the power of 3 millimeter square, based on the dress dimension of 140 millimeter by 140 millimeter. Therefore, the select a 150 millimeter by 150 millimeter post for this. Okay guys, example 9.5. An S4S timber column, nominal 6" by 6" is subject to a compressive load by 22,000 pounds as shown in this figure. The column is supported by a 2 feet by 2 feet square concrete footing that is in turn supporting the soil. Okay, supporting the soil. A, compute the bearing stress on the contact surface between the column and the footing. So stress between column and footing here. And B, bearing stress based on the footing and the soil. Okay, and the example wants us to neglect the weight of the footing and the column. So it's pretty simple, right? So for A, we need sigma equals P over A. All right, and we do have the P, which is 22,000. So 22,000 pounds. And how much is A? 5.5. So 5.5 equals 727 psi. All right. For B, same thing. Sigma equals P over A. 22,000 pounds over, how much is the A? So 2 feet by 2 feet. Each feet is each feet equals 12 inches, right? So 2 feet is 24 inches to the power of 2. The answer is 30.2 psi. So this is the first answer. This is the second answer for B. Since the bearing pressure stress on the soil is generally expressed in pound per square foot rather than pound psi, so if we want to change psi to psf, we just have to multiply it by a certain number. So we say 38.2. What was psi? So psi is pound on square inch. If you want to change it to psf, which is pound per square foot, we have to multiply it to 144, which is square to feet square. The answer is 5,500 pounds per square feet. Okay, this is example 9.6. Before going down to example 9.6, I got a question and I got an answer, because you guys are not here to answer the question. So just think of this bar. If you have a tensile stress on this bar, okay, without these two holes, how much would be the tensile stress? For example, it is going to be X. And if we have these two holes in this bar, how much is going to be the tensile stress? A different X. For example, we call it Z. Now I got a question. Is X bigger or Z bigger? Just think about it for a few seconds. Definitely, the X is smaller than Z, so the stress on Z is bigger. What does this mean? It means that if we need 20 kIPS to break this pole or break this bar, but if we have two holes in here, we definitely need less than 20 kIPS. It means that if we have more holes in this bar, the strength of this bar is going to be less. But for now, we usually don't consider these areas when we want to calculate the stress in this section. In other sections, maybe in other chapters, I teach you how to use the when we have defects or when we have holes in the bar, how to calculate the stress on those bars as well. But let me just put an example, or let's just do the example and find out how the stress and how the strength of this material is going to decrease when there are two holes in there. So example 9.6. A flat steel bar half an inch thick and 4-inch wide is subject to 20 kIPS tensile load. 2 3/4 inch diameter holes are located as shown, or 1/4 inch as shown in figure 9.7a. Determine the average tensile stress at section AA and section BB. So this is section AA and this is section BB. And neglect the stress concentration adjacent to each hole. So first we want to see how much is the stress if we do a cross section here or even here. How much is the stress? All right, so sigma equals P over A. All right, so how much is our P? P is 20. And how much is our A? So our A is 4 by half an inch. Half equals this is 2, so it is 10 KSI. So this is our stress in AA section. What if we want to calculate how much is the stress in this section? All right, so how do we calculate that? In BB section, first we need to calculate how much is the area. The area is not this much because there are 2 holes inside. So the area is gonna be the whole area minus the areas of the holes. The area of total minus areas of the holes. So how much is the area of the hole? We can say if this is the whole area, it is missing 2 rectangles, right? It is missing 2 rectangles from the area. How much are those rectangles? They are 1/4 inch equals 1/2 inch. Okay, so the whole area, which was 2 inches square minus 2 of the 1/4, which is 0.75, half, equals 1.25 inch. Okay, now we have A. We have our A, and we already had our P. Sigma equals 1.25 square equals 160 KSI. What does this mean? Means that the stress on this section, if we cross this, the stress on this section is more than the stress on other sections. Why? Because we have these 2 holes. The strength of this material is lower in this section. The strength of this material is higher in this section. Okay, example 9.7. A 25 millimeter diameter bolt extends vertically through a timber beam. So this bolt is inside a timber beam, as shown in this figure. The maximum tensile stress developed in the bolt is 83 megapascal. Determine the minimum required diameter for the circular steel plate that is to be placed under the head of the bolt. The bearing stress on the timber is not exceeding 3.4 megapascal. So, as you can see, this is our bolt. Our bolt is inside this beam, all right? And we want to put a steel plate or plate washer under this bolt, all right? And we want to know how much the diameter of this bolt, of this plate should be. So this is the exact thing, the plate washer that we want to use under this bolt. So this is bolt and this is the washer, and we want to determine the diameter of this bolt. All right, so for this say P equals sigma A, and we want to determine how much is the A. So the A of the area is pi r2, all right? Area equals the D in here is 25, so the R should be 12.5 millimeter. So pi 12.5 to the answer is 491 millimeters square. Okay. All right. And what do we have from the question? From the question, it says the maximum tensile stress developed in the bolt is 83 megapascal. And as we always do, we want to just convert it to Newton per meter square. So 83 megapascal, if we want to change it to Newton per square meter, we have to multiply it by 10 to the power of 6 Newton. And since this square meter, we want to convert it to a square meter, right? 10 to minus 6 square meter. We just convert this to a square meter, and the answer is 40,753 Newton. All right, now we have the all the answers, so we gotta know how much is the area. Area equals P over the maximum of sigma equals, so how much is our P? 40,753. And how much is our sigma? In the question, it indicates 3.4 megapascal. So 3.4. Since this is Newton, we have to convert it to Newton meters. 10 to the power of 6 Newton meters. The answer is 11.986 to the power of 6 meters. But if we don't want to say it in meters, we can say it in millimeters. So we can say it is 11,800, sorry, 986 meters square. All right. Now, we have the area. We have the area of this washer. We want to know how much is D for this washer, right? So the area of the hole equals the area of the plate, minus the area of the bolt. What we're basically doing is, since we have this plate washer, and since there is a hole inside, this is the area that we have. All right. So we have to calculate the area of the bolt and the area of the whole plate to see how much is the D. So we can simply say A equals, since the area is pi d24 minus pi d24. This is the bigger washer, and this is the bolt. All right. So how much was our A? A was 11,986 equals pi divided by 4 is 0.7854. D2, we don't have the D. This is the D that we want, right? Minus pi divided by 4, which is 0.7854. How much is the D? This D is 25 millimeters. 25 millimeters, power of 2. And if we do the calculation, our required D is gonna be 126 millimeters. So we need a 126 millimeter plate washer to put under this bolt, so this system would work. Okay. Example 9.8. 100 feet long steel bar is suspended vertically from its upper end. The cross-sectional area of the bar is 4-inch square, which is 2 by 2 inch. The unit weight is of the steel is 490 pounds per cubic foot. Let me just write it down. Weight is 490 pounds per cubic foot. Compute A maximum tensile stress due to the bar's own weight, and B, the maximum load that can be safely supported at the lower end of the bar that allows the tensile stress that if the allowed tensile stress is 24,000 psi. So first we're going to calculate A, which was compute the maximum tensile stress due to the bar's own weight. So if you want to calculate the weight per foot for the bar, you have to use this equation. So we say weight per foot equals volume into the weight of the unit. So for the volume, uh, two inch by 2 inch, 12 inch, and if we want to convert the length of the 1 foot to cubic foot, we have to divide it by 12 cubic foot if we want to convert it. How much was the weight of the thing? It was 490 foot cubic feet, and the answer is 13.625 pound feet. All right, now we have all the things that we need. So if you want to know how much is the P, we have to multiply this by the bar's height. So 13.61 into 100 is 1,361 pound. That's our P. Now we have all the things that we need. We have A, we have P. Now we can calculate sigma. P on A. So we have P 1361, and we have our A square pound. Answer is 340 psi. So this is for A, the stress of the weight of its weight itself. And what was part B? Part B is asking us the maximum load that can be safely supported by the lower end of the bar if the allowable tensile stress is 24,000 psi. So how much load we can put on this cross section that it does not break. Okay, so if you guys remember, for that we have to use this equation. P equals A. All right, Just one thing. The bar itself already has this much stress on it because of the weight. Okay, so if we want to add 24,000 stress on the bar, so we have to take this out of the whole number. What do I mean by that is P equals, so 24,000 I minus 340 psi by A, which is 4. The answer is 94,640 pounds. So just one more time. If we want to know how much is the maximum, if we want to know how much is the maximum load, how much is the maximum load that this bar can endure, and if the stress, the allowable stress, is 24,000, because of the weight of the bar, it already has 340 psi stress on it. Okay, so we have to take this out of this number. We have to subtract this number out of this number. All right, which is going to be our total sigma. So the final answer is 94,640 pounds.